Okay, we're going to take a look now at how definite integrals relate to antiderivatives. So everything we're going to take a look at here, it's really important to understand that this is just notation we're going to use here to make this connection between definite integrals and antiderivatives. It's not anything you're ever going to have to recreate. So for these first few slides here, you should just be trying to make sense of what we're looking at here. So we're going to use the notation a sub a of x to denote the area under the curve from a, which is a constant, to x, which could be any number. Okay, so we have the area from a to x. We have that shaded there in blue. And we could also look at the area from x to x plus h. And so we'll denote that a sub x of x plus h. And the entire interval then, if we went all the way from a to x plus h, would be a sub a of x plus h. And if we add these two together, so notation aside, all we're saying here is that the area of the piece on the left plus the area of the piece on the right equals the entire area. And we can rearrange this. We can now say that the area from x to x plus h equals the entire area from a to x plus h minus the area from a to x. Okay, now if we look at a portion of this curve from x to x plus h, if we are trying to find the area underneath there, the minimum value of that area would be found by finding the smallest value of the curve over that interval and creating a rectangle to find the area. And the largest area possible would be found by using the largest value of f over that interval. The true area underneath the curve is somewhere in between those two. So we have that short rectangle found by the minimum value of f, we have the tall rectangle found by the maximum value of f, and the true area lies somewhere in between those two. Okay, so there's a width of h on this interval here, so the area of the smaller rectangle would be h times the minimum value of f. The area of the larger rectangle would be h times the maximum value of f. And the true area, using our notation from the previous page, is a sub a of x plus h minus a sub a of x. And if we divide everything by h, we get this inequality right here. And maybe at this point, you're starting to see something that looks kind of like our definition of derivative. Okay, if we make that value of h really small, so we make that interval very, very, very narrow, approaching a width of 0, the minimum value of f and the maximum value of f get closer and closer together. So if we take the limit as h goes to 0, this is going to equal the value of f of x, because the minimum and the maximum are going to become the same. And now this right here is our definition of derivative of the function a sub a of x. So the derivative of the area from a to x equals f of x. Which means the area from a to x equals the antiderivative of f, we'll call that capital F, plus some constant c. Now if we plug in our initial value, a, the area from a to a is 0 because there's no width to that interval, which means c equals negative f of a. So the area from a to x equals the antiderivative of f at x minus the antiderivative of f at a. So here's our connection between antiderivatives and definite integrals. The area underneath that curve can be found by taking the antiderivative at the right endpoint minus the antiderivative at the left endpoint. So using our notation here for definite integrals, the integral from a to b, which we know from our previous lesson as being the area underneath the curve of f of x from a to b, is equal to the antiderivative of f at b minus the antiderivative of f at a. So now we can evaluate definite integrals. We can find the area underneath the curve for any function just by finding its antiderivative. So let's take a look at this with y equals x squared. This is something that prior to today we couldn't find the area underneath because we don't have any geometric formula for that. But if we want to find the area from 1 to 2, so the integral from 1 to 2 of x squared dx, well, we take the antiderivative of x squared, that's 1/3 x cubed, from 1 to 2, and we evaluate that at 2 and at 1, and we subtract, and we find that the area underneath that curve is 7/3. Now we could do this on our calculators as well. So go to this button right here next to your catalog, find the symbol that looks like a definite integral. You can plug in all the parts, and the calculator can come up with this as well. Okay, here we want to find the area between the x-axis and y equals cosine of x. The way we want to interpret that question is that we're treating all area as positive. If we just took the definite integral, it would treat that first area from 0 to pi over 2 as positive, and the second area from pi over 2 to 3 pi over 2 is negative. But we just want to find the total amount of area. So we want to split this up into two separate integrals. One from 0 to pi over 2, and then we're going to subtract the integral from pi over 2 to 3 pi over 2, because we know that that integral is going to give us a negative value. If we subtract a negative, we'll get a positive. And we can evaluate these by taking the antiderivative, plugging in our limits of integration, and we find that the total area is 3. Now, if we wanted to find the same thing on the calculator, we could, instead of finding where we have our sign change here at pi over 2, we could just take the integral of the absolute value of cosine of x, because that would turn all of the values of that function into positives and make it so that the entire area is positive. And again, we'd get 3. Okay, a couple of rules we have for definite integrals. If we take the integral from a to b of f of x, that's equal to negative integral from b to a of f of x. So if we switch the limits of integration, we change the sign. If we take the integral from a number to itself, that's always 0, because if we think of that as area, it's the area from a to a. There is no area, so 0. If we have constant multiples, we can move those inside or out of the integral. We can add and subtract functions within an integral. So the integral from a to b of f plus g is the integral of f plus the integral of g. All right, and finally, intervals can be added or subtracted. So if we take the integral from a to b plus the integral from b to c, that's the same thing as the integral from a to c. So we can visualize that right here. There's our integral from a to b and b to c, and you can see clearly that that's the entire area from a to c.